It is the 26th of August at roughly 8 a.m. Today we're going to be starting a new chapter from Dummett and Foote on an introduction to group theory. Chapter 1, Intro to Group Theory. So what's the historical context of this? Well, the group concept arose from several streams, namely number theory, addition modulo n, and multiplicative units modulo n, geometry, symmetries, rigid motions of regular figures, permutation theory, Galois' analysis of permutations of roots of polynomials. The axioms isolate the common algebraic pattern in these examples, which we will get into. So for now, let's just look at a definition here: binary operations. So a binary operation on a set G is a function asterisk mark such that product G and G, Cartesian product of G and G, maps to G for AB in the set G. We write A asterisk B or star B for coordinate gotten as AB. Let me check. Now let's look at some of the properties of a binary operation star. Well, a binary operation on G, on a group G. So, a binary operation on G is, for one thing, associative. If A star B in parentheses times, star C is equal to A star parentheses B star C. And that's for all, that's what this means, for all A, B, C within G. Now, it's also commutative if A star B is equal to B star A for all A, B within G. Let's look at a calculative to get at this more concretely. So, looking at binary operations, let's try and see some with the associative or commutative properties that we mentioned earlier. So, this first example, binary operation. associative, additive, associative, and commutative. Now for this next one, this is addition on the integers, subtraction on the integers. Not a binary operation. Reason being, subtraction is a binary operation. But is neither associative, because the parentheses matter. If the parentheses matter, associative or commutative. Now, let's look at the positive integers. With regards to subtraction, that's not a binary operation. Reason being, you can find just a counterexample here. 3 minus 5, that's not within the positive integers. Right. Oh, and this is 1.1, section 1.1 in the book, basic axioms and examples. So, moving on to groups, the concept which this chapter bears the name of. Definition of a group. A group, doesn't really matter, but capitalization. A group is a set G with a binary operation such that we have associativity for all A, B, C within group G. Parentheses. If I said parentheses matter back then, I guess I was trying to say something else, but parentheses don't matter. Parentheses don't matter. Yeah, parentheses don't matter is what I was supposed to say back then. I think I said parentheses matter back then. But yeah, the parentheses don't matter here because you see A star B star C with the parentheses on the A, B is equal to A star parentheses B star C. So that works. It's associative. Identity. So there exists E within G, let's take E to be our identity, such that A star E is equal to E star A, which is equal to A for all A within G. I already tell that's gonna, this is gonna be, there we go. Very good. Now the existence of inverses. Has inverses. It's binary operation. Good, such that it's associative, has an identity, contains inverses. Has inverses. For every A within G, group G, there exists, that's what this symbol means, there exists an inverse of A within G with A star A inverse equaling A inverse star A, which is equal to the identity. Now, here's a bit of a caveat, bit of a supplement. If A star B is equal to B star A for all A B within the group G, then the group is this thing called abelian, commutative, named after Abel, who we get into briefly in the history of mathematics. For now, we'll just keep his name right there, lowercase, etched into the framework of what math is forever. Or at least until everything's over. But, yeah. So let's get into another calculative. Let's look at this more concretely. All right, so let's say we have the binary operation, positive over any two integers. The identity for this, the identity is going to be 0. The inverse of A is negative A. So that's good. Is it associative? Yeah, addition's associative. So let's move on to the rationals. Rational numbers without the 0 over multiplication, binary operation of multiplication. Well, this is not a group. Reason being, the example, there we have a counter example. A counter example, this being 2, has no multiplicative inverse. No, whoops, not 2, sorry, that's putting something beforehand. The identity, we have identity 1, inverse, of A is A over 1. So that works, actually. There we go. Moving on to the integers without 0 over multiplication. So this is not a group, and then we go to the reference which I mentioned earlier. I read a line ahead from my notes. But the example being 2 has no multiplicative inverse in the integers. that true? Is that true? Is it true that 2 has no multiplicative inverse within the integers without there being 0? Well, the identity would be, 0. Well, if we were saying the identity was 0, no, it does, because 2 times 1/2. 2 times 1/2 is equal to 1, which is the identity of the integers out that, so that doesn't work. So what example does work? Well, is there a case where you can get 0? Must have fudged this one. Let's just move on for now. Okay, so the set of all residue classes is a finite abelian group of order n. And we'll get into more of what that means. Okay. No, sorry. I was thinking along these lines. So yeah, 2 has no multiplicative inverse because 1/2 is not within the integers. There we go. Good to go. Zero doesn't really have anything to do with it. I guess the reason why 0 is not included is because if you did, it would be kind of a problem. Because what times 0 gets you 1, right? So, okay, now property. Let's look at some basic properties, starting with this proposition on uniqueness and inverse algebra. So let's just say G is a group. Then we have the identity element is unique. Each A within G has a unique inverse. So the inverse of A is equal to A for all A within the group of G. And we have that the inverse of the product of AB is equal to the inverse of B times the inverse of times the product of each inverse is equal to inverse B times inverse A, which might not be the best way of saying it, but I'm just going to say that in order to say it more easily. For all AB within G. It's not always going to be times or multiplication or anything. It's more just the operation that exists in between these two. So it'd be like B star, right? So yes. Okay, now let's look at a proof of this. Each of these 4 in succession. And Then afterwards we can perhaps look at a calculative example. Okay. So suppose E and F are identities. The Born identities, not just identities. Stealing them would not be a joke. Then E is equal to E star F, which is equal to F by what? By the defining property, by definition. Defining property of F and E. Hence, E is equal to F. Say that? Yes. Okay. So, suppose B and C are both inverses. Of A. Then we have that B is equal to B star E, which is equal to B star parentheses A star C, which is equal to parentheses B star A parentheses C, which is equal to E star C, which is equal to C. And in this we're still staying to the standard of what this thing is. We used the existence of identity E, right there. Identity E, associativity, and the inverse property. By definition, this works. So what do we get from this? Well, inverses are unique. Okay. I need more space. Actually, let's check if that actually shows up well. Shows up well enough. Okay. Oh, this is a continuation of the proof. So 3. Now, inverse of an inverse equaling the actual thing. Since A star inverse of A is equal to the identity, A is an inverse of the inverse of A. By uniqueness of inverses, the inverse of A is equal to A. The inverse of the inverse of A is equal to A. So there we go. Moving right along. So let's for 4, that's the product of elements within a group. The inverse of that, the inverse of a product of 2 elements within the same group being, well, let's get to it. So let X equal B inverse, the inverse of B, the inverse of A. Then what we get is that AB X AB star, you'd say X, we could say is equal to A star parentheses B inverse, the inverse of B star A, the inverse of A is equal to A, this would become the identity element, E inverse of A, which is equal to A inverse of A, which is equal to the identity element. Right, so you can see how that makes sense. Not hiding anything there. Just check. B. Does it quite do it? Does it quite do it though? Let's see. AB inverse. B inverse. B inverse. E. Yeah, the other side of this. Right. Right. So, and then similarly, we do this the other way. X star AB, inverse of B star, inverse of A, B is equal to B, the inverse of B, E, B, which is equal to the inverse of B, B, which is equal to B. So, anyway you slice it, has that. So what can we say about this in particular? Well, we can say that X is a two-sided, no good, rotten, no, a two-sided inverse of AB. And what can we make of that? And well, what we can make of that is that this implies that by uniqueness of inverses, the inverse of the product of AB within the same group is equal to X, which is equal to the inverse of B star inverse of A and QED. Okay. Yeah. Yep. Okay. Because if that's an inverse, then we already know that that was the thing before it was an inverse, and so there's only one inverse. We found it again through different looks. Okay. Now let's look at cancellation and linear equations. Proposition on that. So let G be a group. We're going to be saying that a lot. So we have this notion of left-right cancellation. If AU is equal to AV, then U is equal to V, right? And if UB is equal to VB, then U is equal to V. Left, right, left, left, right, right. Left-right cancellation. Let's move on to the next one. Solving AX is equal to B. So for AB within the group G, the equation AX is equal to B has the unique solution X is equal to the inverse of A star B, inverse of A, B. I'll just say that. From now on, I'll just clump them all together because that's the way it's spelled, I guess you could say. So there we go. Now let's talk about a third one. Solving YA is equal to B. For each A, B within the group G, the equation YA is equal to B has the unique solution Y is equal to B inverse of A. Okay, let's get to the proof of this. So for the proof of 1, if AU is equal to AV, well, simple enough, multiply on the left by the inverse of A to get U equals V. Now, if we have UV is equal to VB, then we can multiply on the right by B inverse to get U is equal to V. Simple enough. Now go to 2. So existence. So x is equal to A inverse B satisfies, is equal to the inverse of A. B satisfies A parentheses A inverse B, which is equal to A inverse B, which is equal to, A, the inverse of A, B, which is equal to the identity element E, B, which is equal to B. Now let's see about uniqueness in this case. Is it a unique solution that we get whenever we use this thing? So, because it makes two claims. One, that such a thing exists. Two, such a thing exists and is unique. Uniqueness. So if AX is equal to B, by left cancellation, we obtain x is equal to the inverse of A, B, and 2 is good to go. So let's move on to 3 using the same sort of logic. Existence, y is equal to B, the inverse of A, satisfies B inverse of A, which is equal to B inverse of A, which is equal to B identity, which is equal to B. Is this proven uniqueness? If YA is equal to B, then we can use right cancellation. Then by right cancellation, y is equal to B inverse of A. Boom, bada bing. And that does it for the proof of these properties, for this proposition. Right? Now let's look at a more close look at a generalized associative law. And let's start with this proposition on bracket independence. So this says that for any n greater than or equal to 1, and any a sub 1 all the way up to a sub n within G, the product a sub 1, a sub 2, all the way up to a sub n is well defined. Remember, we went over well defined. well defined, which is independent, in this case, independent of parenthesization. There we go, big word, bigger word, bigger word. So what's the proof of this? So this is to say, product is well defined. It doesn't depend on what the specificities of the thing are within there. It's as long as it follows these generalized conditions, this thing will work. It's logically consistent to the max on what this thing is supposed to do. So let's get into the proof of why that is. Induct, well, with a rough sketch, because we're not going to do the sort of a exact way of induction. So we're just going to say induct on F, right? And so for n equal to 1 or 2, the claim is trivial. Why is that? Well, plug 1 or 2 into this thing, and it's just so obvious, right? It's like that's what something as trivial means. It's like you put it into the thing, and well, if it's A1 or A2, which are we're given those right at the beginning, so we can already say that that's going to be the case. So in a way, it could be base case, right? But let's move on to n equal 3. So for n equals 3, it's precisely associativity. We've introduced 3, so now we have the issue of putting these into different parenthetical groups, I guess you could say, but let's not say groups. Parenthetical order. Parenthetical order makes a lot more sense. So let's assume the statement holds up to n equals k. So we're getting a little bit more into that. Let's share over here. Consider any parenthesization. What a word, right? What a fun word that is. Parenthesization of A1 all the way up to A sub k plus 1. Now, so it splits as parentheses A, parentheses B, with A being a parenthesized product of the first R terms, and B equal to, well, the last B of the last k plus 1 minus R terms. For some 1 less than or equal to R less than or equal to k. So let's continue on this. So we are getting a bit more specific into induction than I remembered, but that's fine. I mean, good. So by the induction hypothesis, which is that the statement holds up to n equals k, A is equal to A sub 1 all the way up to AR. Those things close together there, and B is equal to AR plus A sub R plus 1 all the way up to A sub K plus 1. Those things operated on each other in that succession, regardless of their internal bracketing. So any parenthesization evaluates to parentheses A sub 1. Those operate all the way up to A sub R, which operates with parentheses A sub R plus 1 all the way up to A sub K plus 1. And here's the kicker. Just look at this for a little bit, and you can kind of see it coming. But any two such choices that we had there earlier, any two such choices of R correspond to regroupings that are all related. All related by repeated use of associativity. At the outermost level. At the outermost level, which we constructed out of it. So, all values coincide. So, what that means is, more succinctly, therefore, the product is well defined. It's well defined for K plus 1. So we prove it inductively. We had the base case, which were those trivial things, and then we carried it all the way to K plus 1, with the assumption that it holds up to K. And so, ergo, we can say that for any n greater than or equal to 1, and any A sub 1 all the way up to a sub n within the group G, the product of all of these a's is well defined, independent of parenthesization. There we go. So, about out of time for today. So, for abstract groups, here's a little notation thing that I believe Domit and Foote call to mind. For abstract groups, and this is something that we've already been looking at more and more, we write, for abstract groups, we suppress the star symbol, the asterisk, and write AB or A star B. For G, for X within G and N within the integer is greater than 0, we define x to the power of n as x, it's in operation with itself here, with n factors, and x to the power of negative n as the inverse of x to the power of n, and x to the power of 0 to be equal to the identity. So nice sweets there. So we'll probably just have time for one last thing before the next section. Okay, so next up on our agenda, we want to look at the order of an element. Start with a nice clean definition. The order of x of the group G, denoted by this absolute value symbol, which is that, is the least n within the integers greater than 0 with x to the power of n equal to the identity. If such an n exists, otherwise x has infinite order. Let's look at a lemma. Characterization. Wait, oopsies. Visibility of characterization. Not characterization itself. Visibility, characterization, of powers. Okay, let's look at that. Let's first of all see what that means succinctly. So let X be an element of the group G, have finite order. Absolute, the order of X is equal to n. Then, for any m within the set of integers greater than 0, x to the power of m is equal to e if and only if, which is what this means, the if with the two f's, n divides n. N divides m. So, proof of this, starting one way, by division algorithm. By division algorithm, right, m is equal to qn plus r with q within the set of integers greater than 0 and greater than or equal to 0. Let's see, q equal to r, I guess. Yes, okay. And 0 less than or equal to r less than n. Then, by division algorithm, you write m is, just erase that because that looks weird. It's me just trying to scratch things out. It doesn't work very well sometimes. M is equal to qn plus r with q being in the set of integers greater than or equal to 0, and 0 is less than or equal to r, which is less than n. Then we can say for any, no. Then we can say x to the power of m is equal to x to the power of qn plus r, which is equal to, parentheses, x to the power of n to the power of q, x to the power of r, which is equal to e to the power of q, right, because I had that earlier. E to the power of q, x to the power of r, which is equal to x to the power of r. Ready then? Yeah. Now, if x to the power of m is equal to the identity element, then x to the power of r is equal to the identity element. By minimality of n, we must have, because it could equal, right? Is it fair to say? Let me see. Finite order such that that is then for any that equals then we must have, then we must have r equals 0. So n divides m, which is what we wanted. Yeah. Okay. Let's move on to the other side of this. So this one is a bit less wordy because we went through it, the bigger one first. So if m is equal to qn, then x to the power of m is equal to parentheses x to the power of n to the power of q, which is equal to e to the q, which is equal to e. So it's a lot more simple proof because we're working backwards from what we wanted here. Because we're already saying that n divides m. Kind of anticlimactic in a way, but it is what it is. I'm not complaining about it anyway. Now let's see another one. So let's look at a corollary. If the order of x is equal to n, which is less than infinity, so it's finite, then the elements the identity element e, x, x squared, on and on and on, all the way up to x to the n minus 1, x to the power of n minus 1, are pairwise distinct. I mean to say, pairwise distinct, and subgroup, this thing, x is equal to the set x to the power of k such that k is within the integers, k is an integer, has cardinality n. Let's go ahead and go about proving that. Right, good. So, if x to the power of I is equal to x to the power of j, with 0 being less than I, less than or equal to I, less than j, less than or equal to n minus 1. So, pay attention to the things up there, right? The exponential stuff that we were working with to begin with, then the elements x squared, all the way up to, whoa, whoopsies. Not yet. Okay, then, sorry, we can say E is equal to xj minus I, with 0 being less than j minus I, being less than n. And this leads to, okay. So this is x to the power of I, x to the power of j, with 0, And then we set up the identity element E. Set up the identity element E here. So let's see. It's equal to j minus I, but 0, but it's greater than 0. It's greater than 0, but it's less than n, and that contradicts the minimality of n. So it can't be the minimal. It can't be the minimal thing, which is what we said it was. Yes, because it can't be the how do I say this? It can't be the cardinality of n, but also include other things outside of it. I mean, like, it can't be the cardinality of x and still be bigger than what we set it out to be with the exact number of elements within x, something like that. My wording is a bit off, but it contradicts, suffice to say that it contradicts the minimality of n. So what we can say is that the subgroup of x, the subgroup of this weird-looking x thing, I wish they had more words, is precisely, well, I personally have more words to access in my mind right now, is precisely the set identity element x all the way up to x to the power of n minus 1, since for any x to the power of k reduces to one of these, which we saw in action by the division algorithm, and the lemma, which isn't up there anymore, of course. Precisely. Yes. Okay. Which was to speak of the divisibility that we had earlier. So hopefully not too much encapsulation with that, but there we go. Which means it has cardinality in it. Because subgroup, not subset. If I said subset, that's essential. Otherwise, we wouldn't be able to use things like minimality or anything like that. So we're working with the identity element. So let's look at a calculative. Orders of familiar groups, orders in familiar groups. So for the integers with the binary operation being addition, which I guess you could say, I should put this down, viewed multiplicatively as that's supposed to be the symmetric difference in simple. Let's see. That meaning n-fold, n-fold. With a to the n meaning n-fold. Every non-zero, so just sort of ignore that for now, but might as well have not put it up there, but oh well. With every non-zero element has infinite order with this here. In Z mod 9, addition over Z mod 9, mod 6, well, 6 mod 9 has order 3. As 6 plus 6 plus 6 is equal to 0. It's nothing. Mod 9. And no smaller. Positive multiple. Oh gosh. Of 6 is 0. Mod 9. That's what that bracket means. So let's look at another one. Let's look at the units. Mod 7 units. So that means over multiplication over the units. Mod 7. 2. So 2 mod 7 has order 3. And this is because 2 to the power of 3 is equal to 8, which corresponds to 1, which is equal to 1 mod 7. Two and 2, let's see here, 2 has order 3, is that, and 2, let's see, it's not equal, 2 itself does not equal that, so 2 is not equal to that 1, so I should say it has an order of 3 because of this. I'm trying to think, like, what exactly was I thinking whenever I put this down? Why did I put that down? It's a while ago. Now, let's move on to 2 more calculative examples. And then we've got to call it quits. Like, we are over time, but we're so close to finishing what I have on the notes, so, you know. Risk it for a biscuit. So let's look at cancellation in practice. Well, we could go to Twitter for that. Not anymore, I guess. Okay, so in modulo, in addition over modulo 12, if a plus x, well, just assume, you know, I'm saying modulo 12 for each of these, right? if a plus x is equal to a plus y, then by adding negative a to both sides, we have x is equal to y. This model model's abstract left cancellation, right? We looked at that earlier. That's exactly what we're doing here with the negative a, except that taking the place of exactly a more concrete. This is the inverse of that sort of thing. So one more, and then we call it quits. So solving ax is equal to b in multiplication over units of mod 12. Units are 1, 5, 7, 11, so if we solve 5x is equal to 7, we just multiply both sides by the inverse of 5. It's equal to 5, by the way, because 5 squared is equal to 1 mod 12. And what we get is that x is equal to 5, 7 is equal to 35, which is equal to 11. And there we go. That completes this section on basic axioms and examples. And that is it for now.